Hello students, good morning. Today you are going to learn a new chapter which is the core of the physics. We can say these topics are core part of the physics, that is electrodynamics. So, this is the core part of the physics, and here it consists of totally 3 chapters, important chapter, moving charges and magnetism. Sometimes it is also called magnetic effects of electric current. Because another name, some textbook they say magnetic effect of electric current, and second one electromagnetic induction, after that alternating current and AC circuits, tell electromagnetic waves. Okay. So, this is generally we call it as the electrodynamics. Okay. So, let us start today the first important chapter of the electrodynamics, that is moving charges and magnetism. So, moving charges and magnetism. So, moving charges and magnetism. Moving charges and magnetism. Moving charges and magnetism. So, as I told you, some others they will say this is the magnetic effects of electric current. Magnetic effects of electric current. Okay. Another name, some others they will say it as magnetic effects of electric current. Okay. Right. So, here why I say this topic is very important, because of course all chapters are important, there is no doubt in that, because our examination point of view, every chapter we are going to get definitely one or two bits, that is not important here. But these electrodynamics is said to be very important, because here the concepts are somewhat modern concepts. All of them are modern concepts. Okay. So, here this electrodynamics is based on 3 fundamental concepts. Number 1, we know already, when a charge is at rest, it produces electric field, that we know already. A charge at rest, charge at rest. Charge at rest, first one, charge at rest, charge at rest, produce only electric field, only electric field, only electric field, very important here, only electric field. When we take a charge or a charged body, it produces only electric field. Next, charge moving uniformly, moving charge, charge moving uniformly, charge moving uniformly, charge moving uniformly, moving means in motion, that is uniform motion, uniform motion means you know already. Uniform motion means what? Velocity is constant, both magnitude and direction, because velocity is a vector. So, both magnitude of velocity and direction of velocity remains constant. then we say it is uniform motion. Therefore, a charge in uniform motion produce electric and magnetic fields, both electric and magnetic fields. Magnetic field, electric and magnetic field, right? So when a charge is in motion, it produces both electric and magnetic fields, right? Next, third concept. Third concept here, that is the third concept that we are going to discuss here is, now let us take a charge accelerating. A charge accelerating. Accelerating charge. Accelerating charge. Accelerating charge. So accelerating charge not only produce electric field, magnetic field, but also radiate energy. Also radiate energy. So produce electric and magnetic field. Not only produce that, not only it produce electric and magnetic field, but also radiate energy. It's very, very important. Whenever a charged particle is accelerate, that not only produce electric field, but magnetic field, but also it radiate energy. Continuously it is going to radiate energy. So these are the three concepts on which the complete electrodynamics has been built up. So first one, a charge at rest produce only electric field. A charge in uniform motion produce electric as well as magnetic field, and an accelerating charge not only produce electric field and magnetic field, but also radiate energy. So that is the three concepts on which this electrodynamic is based on, right? Now, before 19th century, that is till we can say mid of 1800, 1820, 1830, that is we say the beginning of 19th century, scientists have a opinion that there is no relation between electric field and magnetic properties. Electric property is a different entity and magnetic property is a different entity. There is no relation between electric and magnetic effects. Means no relation between electric and magnetic fields. Okay, that is they are entirely different. So a Danish physicist named by Ørsted, Johan Christian Ørsted, a professor at the University of Copenhagen, Denmark, he wanted to demonstrate in his class that there is no relation between electric field and magnetic fields, no relation between electric effect and magnetic effect. So for that, he is conducting one small experiment to prove there is no relation between those two quantities. They are entirely different entities of a physical object. So for that, that generally popularly we call it as the Ørsted experiment. That is said to be as the Ørsted experiment. So let us see what is this simple arrangement for Ørsted's experiment. Ørsted's experiment. So it is called, popularly known as Ørsted experiment. See, it is a simple experiment he want to perform. What he has done is, he has taken one thick wire, a conducting wire. He has taken one thick conducting wire, that is, generally in those days he has taken a copper wire, thick copper wire. Then this copper wire is kept on, made to stand on a small wooden, the bench. So it is kept on the wooden bench like this. He kept on the wooden bench. Then this wire is connected to a key. Here he connected to a key. So here there is a key, and this key is connected to a adjustable resistor. It is connected to an adjustable resistor. He connected to an adjustable resistor. Here it is an adjustable resistor. Okay. So adjustable resistor, and this generally we call it as a rheostat. This adjustable resistor is called the rheostat. So that rheostat is connected to a battery here. It is connected to a battery. So here it is connected to a battery, and this battery is connected to the wire. Now what he has done is, on the same table he has taken one stand. So this is the stand. To this stand, through a thread, he suspended a magnetic needle. He suspended a magnetic needle. He suspended a magnetic needle. Now, means actually what is his idea? He is conducting the experiment to prove that there is no relation between electric property and magnetic property. That is, electric field and magnetic field. Electric property and magnetic property means what? Electric current and magnetic effects, magnetism. Electricity and magnetism. He want to prove that. Now, so see this one here. This is our North Pole. So this is a North Pole here, and this is the South Pole. When the switch is closed, when the key is closed, to his surprise, it was found that magnetic needle is deflected. The moment switch is closed and current is passing through the wire, there is a deflection in the needle. Now, when the direction of current is reversed, means deflection is in this direction now. Current is going anti-clockwise direction. Deflection is toward the, you can say, anti-clockwise. And when the current is reversed, when the direction of current is reversed, now the deflection is also reversed. The deflection is also reversed. Magnitude is same only. The angle through which it is turned is same only. But the deflection is reversed. That is the first observation Oersted has observed in the experiment. And another one, second important observation, this magnetic needle always align perpendicular to the direction of the flow of electric current. Means, suppose this is the direction of current. Suppose wire, current is carrying like this. This magnetic needle, suppose this is the magnetic needle. This magnetic needle is aligning perpendicular to the direction of the flow. Current is flowing in this direction or in this direction. The magnetic needle is coming perpendicular to the direction of the flow. It is perpendicular to the direction of the flow. Means what? Suppose this is the plane, the needle is coming like this, perpendicular to the direction of the flow of the current. That is second observation, that is the second important point that Oersted as observed. Third one, this magnitude of deflection means the angle through which the needle is deflected depending upon the strength of the current. More the strength, more the deflection, less the strength, less the deflection. That is the three important points that has been observed by Oersted during his experiment, which we call it as the Oersted experiment. So from this it has been observed that there is a definite relation between electricity and magnetism. Electricity and magnetism. So that is the fact which leads to the present core area of physics, which we call it as the electrodynamics, or the magnetic effects of electric current or moving charges and magnetism. So that is the basic basis for our present chapter, that is the Oersted experiment. So during Oersted experiment, it was observed, number one, whenever current is flowing through the conducting wire, there is a deflection in the magnetic needle. Number two, the magnetic needle always align perpendicular to the direction of the current flow. And number three, the deflection magnitude, the angle through which the magnetic needle is deflected, depends upon the electric current strength. The strength of the electric current, more the electric current, more the deflection, and less the electric current, less the deflection. That is the three observations made by Oersted. That is, the magnetic field encircle the conductor. Perpendicular to the magnetic needle, coming perpendicular to the conducting wire means the magnetic field lines are encircle the conductor. Means what? Suppose this is the conductor, the magnetic field lines are like circles, concentric circle around this conductor. That is the meaning of this magnetic needle aligning perpendicular to the conductor. That means the field is encircling, means like a circle, concentric circle around the conductor. So that is the major observation during the Oersted experiment, right? Now, what is actually electricity and magnetism? Are they different for one object, or they are one and the same? What are these electricity and magnetism? Electricity and magnetism are, we can say, two sides of same coin. That is, they are two different, we can say, characters, they are two entities of same object or same entity. So then why we say one is electricity and one is electric field and another one is magnetic field? Why we have given different name? Because that whether a charge produce electric field or a charge produce magnetic field, that depends upon the observers. Depending upon observer, one observer may able to see only electric effect, that is electric field. Another observer may able to observe only magnetic effect. So for that, for example, I will tell you what is the relation between this electricity and magnetism. Suppose there is a current carrying conductor. Let us suppose there is one current carrying conductor. Okay. So there is one current carrying conductor. This is a current carrying conductor, right? So now here say this is the direction of current. I current is flowing in the conductor. Now there are two observers. Let us see this. There are two observers. One observer is standing on the ground. One observer is standing on the ground. This is one observer. here one observer standing on the ground. So he is one observer here. So this observer is standing on the ground. Okay, he is standing on the ground. Means what? What does it mean? What is meaning of this observer standing on the ground? That is inertial frame. He is at rest. The observer is at rest. Now, there is one charge. A charge q is kept here. A charge q is kept here. Okay? A charge q is kept here. So I will take another color here. So a charge is kept here. So this is a charge q, it's a positive charge q. Now this positive charge is projected with a velocity v. It is projected with a velocity v parallel to the direction of electric flow. So it is projected with a velocity v parallel to the conductor. With a velocity v parallel to the conductor. So for this observer, the charge is in motion. Therefore, here this charge will be subjected to a magnetic field and it is going to be deflected toward the wire. Now, follow the point here. The charge is in motion now. For observer on the ground, say observer A, he is on the ground, he is at rest, means inertial frame. Now, the particle is projected with a velocity v parallel to the direction of the current flowing conductor. Now, for this observer, as it is in motion, there is a magnetic field produced by this charge. So, due to that, it is attracted by the conductor. So, the charge will be deflected toward the conductor. Right? Now, let us take another observer. Take another observer now. We are taking one more observer. So, take another observer now. She is another observer. This observer is also moving with velocity v. The second observer is also moving with velocity v in the direction of this charge. Along with the charge, he is moving with velocity v. Now what happens here? Velocity of observer is also v, velocity of the charge is also v. That means what? Now the charge is relatively at rest. The charge is relatively at rest because there is no relative motion between them. When there is no relative motion, we know when the charge is at rest, what this observer observe? This observer cannot observe magnetic field now, but he can observe only electric field. Only electric field, so there will be no deflection in the charge. See, entity is same only, charge is same only, but one observer is observing magnetic field, another observer is observing electric field. Why? Because as the observer state is different, the state of the charge is also changing with the observer, so they feel different effects of that charge. That means electricity and magnetism are two entities of the two, you can say, entities of the same physical quantity. Same physical body is same, but effects are different. That effect depends upon the observers. So based on the observer, the effects are going to change. Okay. So that is the meaning of, that is the relation between the electricity and magnetism, or electric field and magnetic field. Okay. So now that is about the relation between the electric field and magnetic field. Okay. When the charge is in motion, it will produce magnetic field, and when the charge is at rest relative to observer, that produce only electric effect. So that depends upon the observers. Okay. So now here we want to find what is the magnetic field produced due to a current carrying element. A current carrying element. Here the concept is current carrying element. Current carrying element. Current carrying element. Current carrying element. This current carrying element is a vector quantity which we write by IDL. IDL vector. This is called current element. IDL is called current element. It is similar to a point charge in electrostatics. Similar to a point charge in electrostatics. Whatever the effects that are produced in electrostatic by a charge, in electrodynamics the same effects are going to be observed due to this current element. Right. So in this case, this current element direction is the direction of the tangent drawn at that point. So now we want to find what is the magnetic field due to a current element of a current carrying conductor. Some shape, irregular shape, a conductor may have any shape, but now we want to find, we will take one small element which is carrying the current, and we want to find what is the magnetic field produced by that current element at a point. Okay. So that is, to find that we are going to use the famous law that is called Biot-Savart's law. We are going to use Biot-Savart law. Biot-Savart law. So this is just similar to our Coulomb's law in electrostatics. You can compare with that of the Coulomb's law. That means what? For any type of current element or current carrying conductor, we can use Biot-Savart's law, like Coulomb's law. Right? Means whether a conductor is having symmetry or conductor is not having symmetry, whatever its shape, we can use this Biot-Savart's law. Okay? Universal you can say in electrodynamics. Okay? So now what we are going to do is, we are going to take one conductor carrying current. Suppose this is a current carrying conductor. So this is a current carrying conductor here. When we take the current carrying conductor, don't join both the things. For clarity, I am taking a thick wire, so somewhat thick you can say. Now, when we want to find the magnetic field due to this conductor, what we are going to do is, we are going to select one current element, small element. So this is, let us say, our current element. This is the element. So this is what we call current element. So here the current flowing is I, and the length of this element is dl. The length of the element is dl. Now, to know the direction of this, just we will draw a tangent here. We draw a tangent in the direction of current. This is the direction of current, no. For this element, we have to draw a tangent at this point. They are like, just like a point. So this is the direction. Therefore, this is our current element IDL. Current element IDL. Okay. This is the current element IDL. This one. So this is our current carrying conductor. This is our element IDL. So this direction of this element is the tangent drawn at this point in the direction of the current. That is the direction of that IDL. That's why I told you it is a vector. Right. Now, we take only magnitude of that IDL and we want to find what is the magnetic field. For that, both Biot and Savard, when they conduct experiments, this magnetic field produced by the current element depends upon three factors. Number one, here they are able to find what is the magnitude of this current element. Higher the magnitude means larger the magnitude, more the magnetic field. Number two is distance of the point at which we want to find the magnetic field. And number three is the sign of angle made by the element with the point. That is, suppose we want to find the magnetic field at a point. Suppose this is the point, we want to find the magnetic field here. Suppose this is the point P. Now, the distance of this point from the element, let us say it is equal to d. Perpendicular distance, shortest distance, that is very important. Shortest distance of the element from the point is d, let us say. Right. Now we want to find what is the magnetic field due to this element here. Now, when we take this element, suppose here it makes an angle. Suppose this is at an angle, let us say. So, this makes an angle. Now, what I am doing is, I am taking one more element here. This element now, this point is at a perpendicular distance d, and this element when I take, it is at a distance r. Right. The distance of the element is r and the perpendicular distance is d, means shortest distance is d from the conductor, and the distance of the element from the point is r. Now we want to find what is the magnetic field at this point. Now let us suppose this dl is making an angle, r making an angle theta with dl. That position vector is there? No. That position vector is making an angle theta with the direction of dl vector, because this r is a vector, dl is a vector, both are vectors now. Position vector also we know vector that indicate the position of this point. Therefore, the distance is r between the element and the point where we want to find the magnetic field, and the angle made by r with the dl is theta. Right. Now see here, what we have here, as this is theta, we can say this is 180 minus theta, because it's just like a straight line here, and this is perpendicular distance we are saying no. That means what? This is 90 degree now, isn't it? Therefore, this will become 90 minus theta, this angle, 90 minus theta. So, what I am doing here, I am taking this element from this point at a distance L. So, I am taking like this now. This is my element. So, see, this is my element, and this wire is at a perpendicular distance d, and the point is at a distance r. This is theta, this angle is theta, and this element what I have done is, from the center of the conductor I have taken at distance L. The element is taken from the center of the conductor. This is the center of the conductor. This is not the element what I have taken now. This is not the element. This is the element what I have taken, and this is the center of the conductor, which is very important here. From center I have taken element at a distance L. So, this is perpendicular distance d, this is our point P, this is r. So, this is 180 minus theta by get just like a straight line here, and this is 90 degree. Therefore, this will become 90 minus theta, isn't it? 180 minus theta, 90. So, 180 minus of 180 minus theta plus 90. So, remaining will be 90 minus theta. Now, our aim is, according to Biot-Savart's law, the magnetic field that is magnetic induction due to that element mu naught by 4 pi into I dl sine theta divided by r square. Divided by r square. This is Biot-Savart's law. I told you, 3 factors by r square. Mu naught by 4 pi into I dl sine theta by r square. So now what is our aim here? We want to find what is the magnetic field due to this conductor. Due to this conductor, one end to another end, where one end of conductor is making an angle theta 1 with dl, another end is making an angle theta 2 with the other end of the conductor. Okay. So for that, what we want to find is, first we want to find dl, then we want to find r. So how can I find dl now? See this diagram, this is L, isn't it? This is d, we know d value. D, shortest distance is fixed. Therefore, we can write, see this, tan 90 minus theta. Tan 90 minus theta, L by d, isn't it? Therefore, we can write L equal to d cot theta, isn't it? Tan 90 minus theta will be cot theta. Therefore, L equal to d cot theta. So what is our dl? Differentiate that. D is a constant here. So d into cosecant square theta. That is our dl value. Next, what is our r value? See the r value now. We want r value. So for r value, what is cosecant theta? When I take, see this, cosecant theta, then what you will get? I want this r value, no. Therefore, we can write here r is equal to d cosecant theta. Right. So substitute in that, what you are going to get now? dB is equal to mu naught by 4 pi into, substitute our dl value, dl. dl is how much? D cosecant square theta, d cosecant square theta divided by r is d cosecant theta. So d square, d we have again r square. So this is also d square cosecant square theta here, d square cosecant square theta into, we have sin theta there extra. So into sin theta. Therefore, into sin theta. So cosecant square theta cancel, d square gets cancelled. Then we are able to get here mu naught by 4 pi into I by d sin theta. That is dB, isn't it? So what do we want? We want the total field, no. So when we want total field, here we are going to get integral of dB equal to integral of theta 1 to theta 2 sin theta d theta. Right, sin theta here also, you have to put d theta, because here also you have to put d theta. Right, because cot theta we have cosecant square theta, but what about this theta? Theta is a variable, therefore differential of that will be d theta. So this is our equation. Now we know integral of sin theta is minus cos theta. Therefore here mu naught by 4 pi I by d is a constant, so we can take that out. Mu naught by 4 pi into I by d into minus cos theta between the limits theta 1 to theta 2. So that will be how much now? Here we can write mu naught by 4 pi, mu naught by 4 pi. So mu naught by 4 pi into I by d into minus of cos theta 1 minus of minus plus cos theta 2. right. So, that is finally is what is our answer now. So, B is equal to, due to complete conductor, we can write mu naught by 4 pi into I by d into, we have cos theta 1 minus of minus plus we have here. So, cos theta 1 minus cos theta 2 minus cos theta 1, or cos theta 1 we can write minus outside, cos theta 1 minus of minus, that is plus cos theta 2. Therefore, B is equal to mu naught by 4 pi into I by d into cos theta 1 plus cos theta 2. So, that is the magnetic field due to a conductor of length L making an angle theta 1 and theta 2, right. Now, suppose we want to find what is the magnetic field on the bisector of the wire. We want to find on the bisector of the wire, right. So, when we want to find B on perpendicular bisector, on perpendicular bisector, of the conductor. Suppose this is the conductor, we have perpendicular bisector we are taking now. That means what? Suppose total length is L, this will be L by 2 and this will be L by 2. This is our D now, isn't it? So, what is our R value now? This is our R value. So, R value will become L by 2 whole square plus D square. Therefore, square root of L by 2 whole square plus D square, that is equal to L square plus 4D square under root divided by 2, isn't it? That is our R value. Now, substitute there in that, then we get B is equal to mu naught by 4 pi into I by d. Now, cos theta 1 and cos theta 2 will be same only, because we are finding out on the perpendicular bisector. So, this is our theta 2, both are equal. Therefore, we can write now cos theta equal to, we are writing as this theta 1, no. Therefore, it is L by 2 by square root of, we have L square plus 4D square divided by 2 plus cos theta 2, L by 2 by L square plus 4D square under root by 2. So, what is our final answer here? See this, L by 4, isn't it? L by 4. So, L by 4 into this L square plus 4D square in the numerator. Therefore, on perpendicular bisector, we are going to get B is equal to mu naught by 4 pi into I by d into L by square root of L into, we can write here 4 into root of so root over, we can write here L square plus 4 D square. This will be on the perpendicular bisector of the conductor. Okay. So, that is our magnetic field on a perpendicular bisector. So, using this Biot-Savart's law, we can find for other conductors also. So, that we will see in the next class. Okay.